Good morning, students. Am I audible? Okay. So last class we discussed about shear force and bending moment, right? So of simply supported beam with a point load and UDL. Today we'll discuss cantilever beam. Okay. So let's wait for 1-2 minutes so that others can join. Then we'll start. Okay. So any doubts from the last classes? If you have any doubts, type in the chat box about how to draw the shear force bending moment diagram from simply supported beam with different loads, point load, UDL load, and combination of loads. Any doubts? Okay, let me share my screen, okay? Let me know if it is visible or not.
In this tutorial, I will show you how to draw the shear force and bending moment diagram for a cantilever beam carrying a point load at its
Screen is visible?
Yes, ma'am.
Okay, and audio and video is
free
fine?
end. Consider a cantilever beam of span
Volume is
L
fine of the
fixed
video?
at end A and free at end
Yes,
B,
ma'am.
carrying
Okay.
a point load at end B.
Okay, so today we'll discuss this cantilever beam with point load at the
Consider
support.
a
Okay, so this is the cantilever beam fixed at A and free at B, and we have point load of W at the free end. Okay,
point load at its free end. Consider a cantilever beam of span L fixed at end A and free at end B, carrying a point load at end B. Consider a section XX at a distance x from the free end B and consider the right portion of this section. The shear force at this section will be equal to the resultant of forces acting on a right or left portion of this assumed section as per the definition of shear force. according to which the shear force at any section XX is equal to the summation of all the forces acting either to the right or to the left of that section. But the resultant force acting on right portion of this section XX is W, which is acting in downward direction. And since this W lies in right portion of XX, it will be considered positive as per the sign conventions of shear force diagram, which we have already gone through in our previous tutorials. Hence, this shear force at section XX is positive. Let Fx be the shear force at this section XX. Hence, Fx will be equal to plus W. Since W is the resultant of forces acting on right portion of this section XX, the resultant is positive. Since the shear force at this section XX has to be positive as per the sign conventions of shear force diagram. Now for drawing the shear force diagram, we will start from drawing the span AB of the cantilever beam. And now we understand that at point B the shear force will be equal to plus W, and since we have derived already that shear force at any section between point B and A will be equal to this plus W, so we will draw this plus W to some scale, and this will remain constant from B to A. Hence this will be our shear force diagram. To make it clearly visible for you, our shear force diagram will look something like this. This is the baseline, and since the shear force is positive, that's why our diagram is drawn above the baseline. Let mx be the bending moment at section xx. The bending moment at xx will be given by mx equal to minus times this point load w into this distance x from section xx to this point load w. The bending moment will be negative as the moment due to load w will be clockwise for the right portion of this section xx as per the sign conventions of bending moment, according to which the beam will bend in a way that convexity will be at the top. From this equation mx equal to minus wx, it is clearly evident that the bending moment at any section between A and B is directly proportional to the distance of section xx from free end B, which means as we go from B to A, the bending moment will increase and this bending moment will be negative. At x equal to 0, that is at point B, bending moment will be 0. And at x equal to L, that's at point A, bending moment will be equal to minus WL. Since at point A x will be equal to L, hence substituting this x equal to L in the bending moment equation, we will get the value of bending moment at A equal to minus WL. Hence, bending moment follows the straight line rule, since the derived equation for bending moment relates with the equation of straight line, which is y equal to mx, but here in this case we got a negative slope as minus w, so the bending moment diagram will be drawn below the baseline. Now let's try to draw the bending moment diagram. We will start from drawing the span AB. Now we know the bending moment at point B is equal to 0. So we will mark this point as 0, and the bending moment at point A is equal to minus WL. So we will draw WL to some scale, but since this is negative, so we will draw it below the baseline. And now we will join these 2 points. This will be our resulting bending moment diagram. For a clear visibility, the bending moment diagram will look like this. This will be the baseline, and WL will be drawn below the baseline to some scale, and the bending moment diagram will be negative. So this was all for today. Stay tuned for much more informative and point load at its free end.
So have you understood this part? So we have a cantilever beam with point load at the free end, and the span length of the beam is L. Okay, so what we have to do, we have to consider a section. Okay, I'm considering here in this question, it is considering a section XX at a distance x from the free end. Okay, then the first step will be to find out the shear force due to this point load. So at this position your shear force will be only this W. In this question they are considering the downward force as positive, so your shear force at this XX will be W. As there is no any other points in between A and B, so we'll if you consider a one section XX, that will be enough to find out the shear force or bending moment. Okay. So the shear force diagram will be same throughout the A and B. It will be W. Okay. Next will be for the bending moment also. Between A and B, you have to consider a same section XX at a distance of x, and what will be the movement? It will be this W into this distance. Okay, bending moment about this section will be W into x, force into distance. And as this is in this question they are considering the clockwise movement as negative, so it will be the negative. You can consider positive also, it's up to you. So beam will be negative as the moment due to W will be clockwise for the right portion of X. So sign convention they have considered the clockwise as negative, so it will have a negative bending moment. Okay. This is a sign convention they have considered. So at your x at that is at B, your bending moment is 0, and at x equals to L. If you replace that x, if you replace that x with L, so your bending moment will become W into L. So with these two values, you can draw your bending moment diagram. It will be like triangle. Right, this is downward because we got negative bending moment. Okay, that's why we have negative bending moment. Okay, let's see another problem for the same cantilever beam but with different UDL. Someone is unmute, please mute yourself.
In this tutorial, I will solve a numerical based on our previous
Screen is
tutorial.
visible. Screen is visible.
Yes, ma'am.
Okay. So in this
In which I
problem, we'll see same cantilever beam but three different point loads at different position. Okay, that one was a simple. You have one point load at the end of the beam at the free end. Now let's see a little more complex beam with different point loads. Okay.
Showed you how to draw the shear force and bending moment diagram. We need to draw the shear force and bending moment diagram of the given cantilever beam carrying point loads at different locations. In order to draw the shear force diagram, we need to calculate the values of shear force at points A, B, C and D. And we will start from point D. So shear force at point D will be equal to this point load 200 Newton, and shear force just to the right of point C will also be equal to 200 Newton, since shear force between point D and C will remain constant since there is no load acting in between. Now shear force just to the left of point C will be equal to summation of all the forces in the right portion of this point, which will be equal to 200 Newton plus this 100 Newton equal to 300 Newton. And shear force just to the right of point B will also be equal to 300 Newton. Since shear force will remain constant between point C and B because there is no load in between C and B. Now shear force just to the left of point B will be equal to summation of all the forces in the right portion of this point, which will be equal to 200 Newton plus 100 Newton plus 50 Newton equal to 350 Newton in total. And shear force at point A will also be equal to 350 Newton because shear force will remain constant between point B and A due to absence of any other load. Now for drawing the shear force diagram, we will start from drawing the span of the beam, and as we calculated, shear force at point D will be equal to 200 Newton. So we will draw 200 Newton to some scale at point D. Since the shear force is constant between point D and C, so we will draw a straight line between these 2 points which is parallel to the span, and shear force just to the left of point C is equal to 300 Newton. So we will draw another 100 Newton above this point to make it 300 Newton. The shear force between point C and B is constant and equal to 300 Newton. So we will draw a straight line between point C and B which will be parallel to the baseline. The shear force just to the left of point B will be equal to 350 Newton. So we will draw 50 Newton about this point to make it 350 Newton. And since the shear force between point B and A is
Abhisha,
constant,
mute yourself.
so we will draw a straight line between B and A, which will be parallel to the baseline. And now joining these 2 points, we will get the resulting shear force diagram. For a clear visibility, the shear force diagram will look like this. Now for drawing the bending moment diagram, we will calculate the values of bending moment at all the 4 points A, B, C and D. The bending moment at point D will be equal to 0, and the bending moment at any section between C and D at a distance x from point D will be given by mx equal to minus times 200 into x, which follows a straight line law, which means the bending moment diagram between C and D will be a straight line but with a negative slope. The bending moment at point C is equal to minus times this 200 into 4 equal to minus 800 Newton meter, and the bending moment at any section between B and C at a distance x from point D will be given by mx equal to minus times this 200 into this distance x minus 100 into this distance, which will be equal to x minus 4, and the negative sign is because of the sign conventions of bending moment diagram. Hence this equation also follows the straight line rule, which clearly indicates that the bending moment diagram between point C and B will be a straight line but with a negative slope. At point B, x will be equal to 8. So bending moment at point B will be equal to minus times this 200 into 8 minus 100 into this 4 equal to minus 2000 Newton meter. The bending moment at any section between A and B at a distance x from endpoint D is given by mx equal to minus times this 200 into x minus 100 into this distance, which will be equal to x minus 4 minus 50 into this distance, which will be x minus 8. And hence it follows a straight line law, which clearly indicates that the bending moment diagram between A and B will be a straight line. At point A, x will be 10. So on substituting value of x in this equation, we will get the value of bending moment at point A, which will be equal to minus times 200 into 10 minus 100 into this distance, which will be 10 minus 4 minus 50 into this distance, which will be 10 minus 8. So we will get in total minus 2700 Newton meter. So we got these values of bending moment at different points for drawing the bending moment diagram. For drawing the bending moment diagram, we will start from drawing the span of the beam. And since the bending moment at point D is 0, so we will mark this point as 0. As calculated, the bending moment at point C is equal to minus 800 Newton meter. So we will mark this point as minus 800 Newton meter to some scale, and we will join these 2 points by a straight line, since this span follows the straight line rule. Now the bending moment calculated at point B is equal to minus 2000 Newton meter. So we will mark this point as 2000 Newton meter to some scale below the baseline, and join these 2 points by a straight line, since this span BC follows a straight line rule. The bending moment calculated at point B is equal to minus 2700 Newton meter. So we will mark this point below the baseline as 2700 Newton meter to some scale, and join these 2 points by a straight line, since AB follows a straight line rule. Now enclosing the diagram by joining these 2 points, we will get the resulting bending moment diagram. For a clear visibility, the bending moment diagram will look like this. So we got these values of bending moment at different points for drawing the bending moment. The shear
So
force
in
will
this
remain
beam,
constant. Force and
procedure
bending
will be
moment
same,
diagram of
but
the
you
given
have to
cantilever
consider,
beam
say there is two
carry.
section, right? One, this section A, B, B to C, C to D. So you have to consider a section at C to D, then B to C, and then A to B. Okay, there will be, as there are three segment, 1, 2, 3. So you have to consider three sections. Okay. So shear force at D will be the same as the load is given. Okay. Shear force just to the right of C. That means at this position. At this position there is no any load. Only point load is given. So the shear force will be the same. Okay. Now shear force at C. Shear force at C will be a summation of this load and this load. Okay, 100 plus 200. Shear force at C. Okay, now shear force just to the right of B. That means at this section. At this section, as I have only these two loads, so it will be the same shear force that it has at C. Okay. Now, if I consider at point B, it will have a shear force of 100, 200 plus 50. So it will be your 350. And now between A and B, that means shear force at A will be the same because there is no any other load, instead these three loads. So shear force will be same. So I got my shear force points. So I'll draw the free body diagram with point loads. Okay. So this is my shear force diagram for cantilever beam with different point loads. Now let's move to the bending moment diagram. So this is the way you have to draw your shear force diagram and bending moment diagram. Okay. This is the shear force diagram. Now let's move to the bending moment diagram. You have to take a section between C to D, then B to C and A to B. Okay. So let's start with the free end. So let's start with the free end. Bending moment at D will be equals to 0. Okay. Now bending moment at any section between C and D at a distance x from the D. If I take a consider, suppose, let me note, if I take a section x okay, you have to take a you have to consider section x at a distance x. So here it will, your bending moment will be force into this distance, so 200 into x, and with the sign convention clockwise they have considered negative, so minus 200 into x. Okay, then if I move forward, now bending moment at C, the bending moment at C will be at C, suppose at C, completely at C, so you have force 200 Newton and which is at a distance of 4 meter. So 200 into 4 meter, so minus 800. Now bending moment between A and C, suppose let me consider section XX, which is at a distance of x from the free end. So your bending moment equations will be this force 200 into this distance. So 200 into distance and force into distance. As the clockwise is negative, so minus 200 into x. Now this part is over. Now next force I have 100 Newton, which is at C. So if the whole length is x, how much distance will this will be? We know from C to D is 4 meter and the whole distance is x meter, so I can write this distance as x minus 4. Clear? So now the moment of C with xx will be this 100 into x minus 4. So again clockwise is negative, so minus 100 into x minus 4. Any confusion from this part? Please type in the chat box. Any confusions from this part?
Ma'am.
Okay, thank you. So this is the moment at B to C. Okay, the same will be. Now so this is, they have considered a section, they have found out the moment equation. Okay, now moment at B. Now moment at B, I have these two loads. Now I'm considering this section at XX. So 200 into x, this 200. Okay, movement at B. Okay, movement at B, I have I have distance 4 into 4, which is 8 meter. So 200 into 8 meter. This next 400 this 400 is at a distance of 4 meter. So that's why 400 into 4 into 100. So this is the moment at B. Now if I consider a section of XX in the next part, let me show you. So if I consider a section between A and B, so what will happen? 200 into x, 200 into x, 100 will be x minus 4. Now 50 will be x minus 8. Okay, so this is the moment equation. So place the value of x for different conditions. You will get the moment at different point. Moment at D, moment at C, moment at B, and moment at A. Okay. If you draw a bending moment diagram, it will be like this. Okay, so this is the bending moment diagram for the beam given to us. So you have to draw the bending moment. You can draw shear force diagram also here. Shear force diagram. Then below that you can draw a bending moment diagram. This should be like this. Okay. So any issues, any doubts you can ask for the cantilever beam with point load and different point loads. Any issues?
No, ma'am.
What about others? Only one is replying.
No, ma'am.
Okay, okay, you can write your roll number. We'll continue with the next class. You can write your roll numbers in the chat box. Okay, after 10 or 15, I'll text in the group, then join for the next class. Okay, anyone left to write? I'll call out the roll numbers once. So check. Okay, 24, 32, 34, 1, 13, 8, 30, 22, 21, 4, 12, 3, 25, 7, 26, 20, 41, 29, 45, 33, 9. Anyone left? Okay. Hope everyone wrote their roll number. So I'm ending the meeting. See you in the next class. Thank you.